Alright, so finally we are going to start chapter 2, which is on velocity, acceleration and scalar angular velocity. The subject goes by the name of mechanics, which is the study of motion of material bodies. It has two parts, kinematics and dynamics. In kinematics, we are only concerned with geometrical descriptions of motion without taking into account what causes motion. Actually, that is force, you already know. So, if we take that also into account, then we get dynamics. Right now we are going to see kinematics. That means we will only be concerned about how we can describe all possible motions geometrically without thinking about forces, that is causes of motion. We will see dynamics afterwards. Next, the author says this: the basic building blocks for bodies, material bodies whose motions we are going to study in mechanics are particles. Bodies are composed of particles. What is a particle? A particle is an idealized body that occupies only a single point in space. When you think of actual things, that means objects in reality, no matter how small they are not like this. They don't occupy only one single location. Instead, they are always extended objects, things that occupy volumes, not just a single point. It can be very small, but we don't see this thing. This means that this is only an abstract concept. Okay, but then how are we going to use this to study motions of objects which are actually extended objects, not point particles? Well, this is how. Suppose you want to study the motion of the planet Earth around the Sun. Because the distances involved are very large, if you look at the system from that scale, the Earth looks like a point, a particle. The Earth is actually very big compared to our sizes. However, in that study, in that situation, the actual shape and size of Earth, they do not matter. Whether you consider it or not, that won't really significantly change anything. So, in practice, a particle is something whose own size and shape are insignificant in a given situation. That's what a particle is. Let me give you another example. Suppose you have an atom in which there is a central nucleus, of course, because that's how things are, and electrons are circling around it. Say the atom is this large. So there are electrons circling around a central nucleus. How large do you think the nucleus is compared to the atom? Is it this large? I mean, if the atom is of this much size, will it be this large like a small marble? Or will it be smaller than that? Actually, you won't even be able to spot the nucleus at this scale. If you enlarge the atom really very much so that it is almost as big as a very big hall, then at the center of that volume, you will be able to just about make out that there is something, that something is nucleus. So it is that small, in spite of the fact that most of the mass of the atom is concentrated at that location. So compared to the scale of the atom, the nucleus is, or it can be considered a particle. Although actually it's not a particle in the theoretical sense, nothing is a particle in this sense. However, in practice, when you do something, then there are objects of insignificant size, they are considered particles. And that assumption does not cause much error. In that sense, we are going to use particles. Okay, so now we have particles. Say you have a single particle, which is something of insignificant size. What are you going to do with it? Say it's moving with respect to some reference frame, something. How are we going to describe its motion? For that, we have two important kinematical quantities, which are kinematical because they do not take into account cause of motion, that is force. and they are of course the particle's velocity and acceleration. We of course begin with the simple case of straight line particle motion. That means motions which are restricted on a straight line. On a straight line, a particle is moving in whatever manner it's moving. I mean, that motion can also be quite complicated. Say the particle moves in a zigzag pattern like this on the straight line, as opposed to say moving in only one direction. But still, we are first of all going to consider that type of motion. And such motions are called rectilinear motion. Okay, motion along a single straight line, where velocity and acceleration, these quantities are scalars. I have put a star here because actually they are not scalars, but you will see that they will look like scalars. Okay, you will understand what this means when we actually define velocity and acceleration for rectilinear motion. And then we will progress to three-dimensional motion. That means motion in space in any manner, where velocity and acceleration are vectors. Here also they are vectors, but they act as if they are scalars. The other important idealization is a rigid body, which we consider as a collection of particles linked by a light rigid frame. So that means a rigid body is an extended body. Okay, here there can be many particles. However, the condition is that they are rigidly fixed in the sense that they do not change their relative positions. The position of any one particle in a rigid body with respect to the other particles that are present there, that does not change, no matter what happens. So you can understand that just like particles, this is also an idealization, because a perfectly rigid body in nature does not exist. You of course have many solids which look rigid. For example, this marker can be called a rigid body. In most situations, it stays like this. It continues to maintain its shape and size, no matter what. But if I make the conditions very severe, then it will lose its rigidity. For example, if I start to hit it with extreme force, it will break. So that way it can lose its rigidity. Or I can start to heat it up, it will start to melt. So that way also it can lose its rigidity. So this is also an idealization. However, still we are going to use it just like we use particles. For example, this can be called a rigid body in normal situations like that, although it's not a perfect rigid body, which anyway does not exist. And the important kinematical quantity in the motion of a rigid body is its angular velocity. And in this chapter, we consider only those rigid body motions which are essentially two-dimensional. That means essentially they happen only in some plane. They do not leave the plane. So that angular velocity is a scalar quantity. So that means this is the simple case. The general three-dimensional case is studied in chapter 16, where angular velocity will be a vector quantity. This is the realistic case. Why do we have to consider angular velocity when the body is a rigid body? And when it's an extended body, it's not a single particle. Well, that is because when you throw a particle, let me put it this way, when you throw a particle, it just moves, it changes its location as it moves. So with that type of motion, you can only associate velocity and acceleration. Whereas when you throw an extended object, there is a rotation also involved, usually. Usually means almost always it rotates as it also goes forward or in whatever manner it goes. So with that rotation, you have angular velocity. Now in this type of rigid body motion, which is somewhat restricted, that rotation happens only in a plane, like this for example. But if it rotates in three dimension in any manner, then that situation becomes complicated, so that we will consider here. So here angular velocity will be a vector because you will have to keep track of how the rotation is happening in space at every instant of time. The axis of rotation itself keeps changing. That's the most realistic situation. And when your body is not rigid, for example, say the individual particles keep changing their relative positions, then you have a fluid, and the corresponding mechanics is fluid mechanics, which you can understand is much more complicated than rigid body mechanics. So now we finally start our study with straight line motion of a particle. Say this is your usual x-axis, which already has the points on it numbered using real numbers or named using real numbers. So there is an origin. This point corresponds to the real number 0. You already know these things, but still I am reminding you. The points that lie on the right side of O have got positive real number names, and the ones which lie to the left of O, they have got negative real number names. These names or real numbers are like labels which help us identify which point is where. Okay. Now consider a point P which actually is the particle moving on the x-axis, moving on this axis such that its displacement x. Displacement x means the position where the particle is. That's a geometric point, and that has a name x, which is a real number. We know that x from the origin O. From the origin O means if you know x, you know where that point is with respect to the origin. In that sense, x is the displacement of P from the origin. Say x is known as a function of time t. That means, of course, as P changes, x also changes. Now we know precisely when x becomes what as a function of time. You give me some time instant, I will tell you what x is at that instant, correspondingly where the particle P is at that instant. The figure may give you an impression that the particle is moving rightward because of that arrow. But that's just a general arrow. I mean, it just shows that the particle is moving in some way. But we discussed just now that even this motion, which is restricted on a straight line, can be quite complicated. For example, the particle may go back and forth like this. It may choose to stop somewhere and remain like that for some time. Anything can happen. And even when it's moving in only one direction, it can do so in several different ways. For example, it can choose to speed up, slow down arbitrarily, stop, and remain like that for some time, and then again choose to suddenly speed up in that same direction. So many things can happen. Now, no matter how the particle moves, we know its position at any instant of time, and based on that, we define this first thing. The mean velocity or average velocity of P over a time interval t1, t2 is defined to be this quotient, this ratio, x of t2 minus x of t1 divided by t2 minus t1. That means the position of the particle at time instant t minus the position of the particle at time instant 1 divided by the length of this interval. Here, of course, you understand that t1 and t2 are two real numbers where t1 is less than t2. Okay, that thing is there. Now let's see this thing next in this example. The example will bring out something about this definition which is not immediately apparent. So in the example, suppose the displacement of P, that means we have this setup, all the same things, the axis, P, O, all these things. The displacement of P from O at time t is given by this formula. X equals t squared minus 6t, where x is measured in meters and t in seconds. We have to find the mean velocity of P over the time interval 1, 3. That means between the time instants 1 second and 3 seconds, we have to find the mean velocity of p if the motion is like this. Solution, the mean velocity of course in this interval is x of 3 minus x of 1 divided by 3 minus 1. And then of course you use what x is as a function of t. You substitute t equal to 3 here, you find minus 9. And if you substitute t equal to 1, you find minus 5. It's a simple calculation. And then finally this is what you get, minus 2 as the mean velocity. And the unit of course should be meter per second. Do you notice this minus sign? What does it actually mean? We are not going to answer this immediately, okay? Instead, let us now next see the counterpart of mean velocity, which is in fact the more important thing for us, that is instantaneous velocity, velocity at an instant of time. Now of course, when you try to define the velocity of something at an instant of time as opposed to over a time interval, you encounter a problem. We can't find the velocity of p at the instant t equal to t1, say, by taking t2 equal to t1 in this ratio, because then you would be dividing by 0. And anyway, this formula cannot be used in this case because it's only applicable when t1 is less than t2, not equal to t2. You can, however, do this. Instead, we define it as the limit of this ratio as t2 approaches t1, i.e., as the length of this time interval tends to 0. That means we define the velocity of p at the instant t1 as this limit of this average velocity or mean velocity over an interval which itself becomes smaller and smaller, provided the limit exists, of course. Now there is something which you may get wrong about this entire thing immediately. Because we have been discussing with this interval where t1 is less than t2, you may think that in this limit also t1 is always less than t2. No, if we are assuming only that, then this would be a right hand limit. However, this means a two-sided limit. So, what can we say about the case where t1 is greater than t2? In that case, what interval is involved? Obviously, that's not t1, t2. In that case, the interval is t2, t1. Okay, so both the time intervals, from both sides of t1, t2 is coming and getting closer and closer to t1. In that way, you consider this two-sided limit. If this exists, then its value is defined to be the velocity of p at the time instant t1. So here t1 is fixed and t2 is changing. However, this is something that you already know from calculus. It's nothing but the derivative of the function x with respect to the independent variable t, that means its own independent variable, at the time instant t equal to t1. And we get definition 2.1, the definition of one-dimensional velocity. The instantaneous velocity, usually when we use the word velocity, we mean instantaneous velocity. If we want to separately mean mean velocity or average velocity, we have to say so explicitly. The velocity v of p in the positive x direction is defined by v equal to dx dt. So here itself you see something which you don't see in the definition of average velocity. But there also it's there. Velocity is measured in the positive x direction. That makes it a vector, although it looks like a scalar, but actually there is a direction. So that minus that you saw over there, minus 2 meter per second, it means that the average velocity is pointing in the negative x direction in that case, in case of that example. But then why are we not treating these objects as vectors? They are vectors, but the fact is that these vectors are either pointing in the positive x direction or in the negative x direction, and that is taken care of by that sign. If the sign is plus, then it's pointing in the positive x direction, otherwise it's pointing in the negative x direction. So there is actually no need to consider that I hat, which in fact we should write. If you want to write this quantity as a vector quantity, it is a vector quantity. If you want to really reveal its nature as a vector quantity, you have to write this times I hat. Okay, so that if this numerically becomes a negative real number, then minus something times I hat, minus something means minus something positive, or in other words, some negative real number times I hat will be a vector pointing in that direction. But because it's either this direction or that direction, so the sign of this numerical part itself takes care of that, so we don't bother writing I hat. That's why it looks like a scalar, and we say that it's a scalar. Okay, so that's the only thing. And the speed of p is the rate of increase of the total distance traveled, and that is why it should be this absolute value of v. Did you notice one more thing? That although this is just a real number, but it's really not the magnitude of the velocity vector. Rather, this is the magnitude of the velocity vector. These bars do not, of course, indicate magnitude, because here you are taking the absolute value of a real number, but it does give you a non-negative real number, not negative, because just like that example, although there we calculated mean velocity, not instantaneous velocity, but still I am saying there you have a minus sign. That cannot be the magnitude of any vector. Magnitude by definition is either 0 or a positive real number. So this is instantaneous velocity and this is speed. Okay. And just like that, you have the next definition of one-dimensional acceleration. The acceleration, or more accurately, instantaneous acceleration of p at the time instant t, of course, that I have not written, in the positive x direction is defined by these equations. Acceleration is the derivative of velocity, or the second derivative of displacement with respect to time, provided this derivative exists. And just like velocity, actually this is also a vector quantity, although it looks like scalar, we just don't write that I hat. That's all. Let's see this example 2 next. Suppose the displacement of p from O at time t is given by this formula. X is the displacement, x is t cube minus 6t squared plus 4t, where of course again x is measured in meters and t in seconds. We have to find the velocity and acceleration at any time t. And we also have to deduce that p comes to rest twice during its journey, and we have to find the position and acceleration at the latter of these 2 times when p comes to rest. Solution: there has been a mistake. X is actually this. We don't have any t here. Okay, I took that down wrongly. You can use that x also, but for that probably this fact is not true. But anyway, we have only 4 here. So then what will be velocity? For that you differentiate x with respect to time and you get this 3t squared minus 12t meter per second. And you differentiate with respect to time once more and you get acceleration, which is 6t minus 12 meter per second squared. So next we have to show that p comes to rest 2 times during its journey. Coming to rest means what? It means having v equal to 0. So if you substitute 0 here, you can already see that there will be 2 values of t, because you get a quadratic equation. So there will be 2 time instants when the particle stops momentarily. And we have to find the later of those time instants and at that later time instant we have to find the position and acceleration of the particle. Now solving this equation v equal to 0, these are the two values of t that we get, 0 and 4. So that means the later instant of time is t equal to 4 seconds. Now we need to find x of 4 and a of 4. And we find that x of 4 is minus 28 meter and a of 4 is 12 meter per second squared, which of course you can calculate using these expressions. What does this mean? It means that when t is 4 seconds, at that time instant, the way the particle is moving, it will be situated 28 meters away from the origin and on the negative side of the x-axis. That's what it means. And acceleration at that instant is 12 meter per second square. So you see that when the velocity is 0, the acceleration is not necessarily 0. Okay, it has a non-zero value. And the author specifically draws our attention to this fact. And finally, let's see another example where this time acceleration will be given. We will find velocity and displacement. A particle p moves along the x-axis with its acceleration at time t given by this expression, 12t squared minus 6t plus 6 meter per second square. Initially, p is at the point x equal to 4 meter and is moving with speed 8 meter per second. Moving with speed, okay, you note this carefully. Speed 8 meter per second, but in the negative x direction. That means velocity initially is minus 8 meter per second. We have to find the velocity and displacement of p at time t. I ran out of space to write that. If we are given displacement, then we differentiate once with respect to time to find velocity and then differentiate once more with respect to time to find acceleration. But if acceleration is given and we want to go in the other direction, we have to integrate. So you integrate this with respect to t and doing that you get this. Plus do not forget that arbitrary constant, okay, because this integration is really antiderivative or indefinite integral. Antiderivative is any one such function. The set of all such functions is indefinite integral. But anyway, so this is something you have got. But how do you find C1? Because C1 here is an arbitrary constant. To find C1, you have to use these initial conditions. Initially, P is at the point x equal to 4 meter. What does that mean? Actually, we won't be able to use this one itself here, but rather we have to use this one because here it is said what the velocity at the initial instant is. Initial instant means when t is equal to 0. At that instant, velocity is minus 8 meter per second because in the negative x direction. So you would substitute t equal to 0 and v equal to minus 8, and that way you can find C1, which actually will be minus 8. So this is your velocity. This expression minus 8. You should write meter per second. Okay, I did not write that. And then to find position or rather displacement, what do? You again integrate with respect to t. You get an expression like this plus again an arbitrary constant C2. To find this one, now you have to use this condition. When t is 0, that means initially x is 4. So you substitute t equal to 0 here, this part vanishes. You have C2 on the right hand side and 4 on the left hand side. So that's how C2 becomes 4. So this is your displacement at time t. Here you put this within brackets and write meter. That's the unit. And let me end this video here itself. In the next mechanics video, which we will see next week, we are going to start general motion, which is not necessarily along a straight line, which can be in any way in 3 dimensions.